Okay, so we all check the weather forecast, right?
Yeah, pretty much every day.
But what if those forecasts were way more accurate?
Oh, yeah.
Like way more detailed and faster, too?
I could tell you not just will it rain, but like
Yeah.
how much rain could we get?
Exactly.
Yeah, that'd be game-changing.
So today we're going to go deep on how machine learning is totally changing weather forecasting.
It really is a whole new era.
Like, forget those giant supercomputers crunching numbers for hours.
Right.
Machine learning is stepping up.
And sometimes even outperforming the traditional methods.
So to unpack all of this, we've got two key papers we're diving into.
Okay, sounds good.
One is all about this thing called residual corrective diffusion modeling for kilometer scale atmospheric downscaling.
A mouthful, right.
We'll just call it CORDIF.
Much easier.
And the other paper is on probabilistic weather forecasting with machine learning.
So looking at probabilities instead of just a single deterministic forecast.
Yep, and that introduces a model called GenCast. But to give some context, we're also going to touch on this third paper about learning skillful medium-range global weather forecasting.
So this will help us see the bigger picture.
Yeah, exactly.
Right.
It uses a model called GraphCast.
Oh, yeah, I'm ready.
So traditionally, right, to get those detailed local forecasts.
Like the ones you see on your phone.
Yeah.
We use something called dynamical downscaling.
Okay, so dynamical downscaling, that sounds kind of complicated.
It is.
What is it, actually?
Okay, so you know how the atmosphere is like super complex?
Yeah, a lot of moving parts.
It's crazy.
Really moving parts.
Yeah, so dynamical downscaling uses these huge computer programs,
Like what?
like the Weather Research and Forecasting Model.
Never heard of it.
It's called WRF for short.
Yep.
And these models try to like simulate every little detail of the atmosphere.
Why detail?
Well, as much as they can.
Oh.
Like looking at temperature and pressure wind and all the physics of how they interact.
Okay, so that has to be like computationally intense.
It's insane.
Like, how much computer power are we talking?
It needs these massive supercomputers running for hours just to crunch all that data.
And it's still not perfect.
Yeah, because weather is so complex.
Right. Hey,
There's still inaccuracies, you know,
yeah, I see.
limitations.
Okay, so if that's the super complicated approach,
Right.
what else is there?
Okay, so there's this other method called statistical downscaling.
Statistical.
It's less computationally demanding.
Okay, good.
So instead of like simulating all those physics,
right.
it just looks at historical weather data.
Like patterns?
Exactly. Patterns and relationships
Okay.
between large-scale weather systems and what happens locally.
So it's like if a big storm system moves through,
Right.
certain areas tend to get hit harder.
Exactly.
Okay.
It basically learns a statistical map
Okay, interesting.
between the big picture and the finer details.
Well, this is where machine learning comes in.
Oh, yeah. This is where it shines.
How so?
So you can think of machine learning downscaling as like a super advanced form of statistical downscaling
Okay.
because it can learn these crazy, complex, nonlinear relationships in the data.
So it's even smarter than the old statistical method.
It has the potential to be much more accurate.
Okay, so that's the basic landscape we're dealing with.
Right.
Now, one of the things that I think is really cool about all this is diffusion models.
Diffusion models.
Yeah, have you heard of these?
Oh, yeah. They're getting a lot of attention.
They're key to understanding both CORDIF and GenCast.
Okay, so why are they so important?
Well, they're this type of generative machine learning.
Generative meaning.
It means they can actually create new data.
Oh, wow.
And they can generate these high-resolution weather scenarios.
Oh, that's cool.
Each with a probability attached.
So instead of just saying, it will rain,
It's like there's a 70% chance of rain.
I like that much better.
Right. It gives you a better sense of what might happen.
More nuance.
And they're already showing some really amazing early results.
Like what?
So there was this one study where they used a diffusion model to predict rainfall intensity in the UK.
Oh, wow.
Based on just the large-scale wind patterns.
Impressive.
Another one looked at predicting solar irradiance in Hawaii.
So how much sunlight would reach the ground?
Yeah, even a day in advance.
Wow, that's useful.
And we're also starting to see them being used for these more general weather forecasts.
That makes sense.
That include probabilities.
Okay.
And for like really short-term forecasting.
Nowcasting.
Nowcasting, yeah.
So like what's going to happen in the next hour?
Exactly. So
But
what makes these diffusion models so good for weather?
Well, for one thing, they tend to be pretty stable
Okay, that's good.
and relatively easy to train.
Which is not always the case with machine learning.
Well, not at all.
And importantly, for what we're talking about today,
Yeah.
they've shown they can generate these kilometer-scale predictions.
Wow. So super localized detail.
Exactly.
That's great.
So how do they work?
Do you want to try to picture it?
I like pictures.
Okay, so imagine you start with just this completely random static-filled image.
Just noise?
Pure noise, yeah.
Okay.
A diffusion model gradually removes that noise,
Okay.
step by step,
Interesting.
until you get this clear picture.
And that clear picture is like the weather forecast.
Exactly.
Okay, I'm following.
And it learns how to do this by studying tons of historical weather data.
Okay, so it sees all these patterns over time.
Right, all these complex relationships between different weather variables.
Where does the probability part come in?
Okay, so because we start with that random noise,
The static?
yeah, if you run the model multiple times,
Okay.
each time, starting with slightly different random noise,
It's like hitting refresh.
kinda,
Okay.
you end up with slightly different forecasts,
Each one's plausible.
equally plausible.
That's cool.
This is how we get ensembles,
Ensembles.
multiple forecasts that show a range of possible outcomes,
Okay.
each with a certain likelihood.
So you're not putting all your eggs in one basket.
Right, you're exploring different possibilities.
Okay, cool. So that's diffusion models in a nutshell.
Right.
Now let's dive into this CORDIF model.
Okay, Cordiff.
Residual corrective diffusion modeling.
So this one's all about getting those super high resolution forecasts.
Kilometer scale, right.
Yeah, the really detailed stuff.
So how does it do that?
Well, it has this clever two-step approach.
2 steps.
Yeah, break it down.
Okay, walk me through it.
So the first step is all about predicting what they call the conditional mean.
Conditional mean, what is that?
It's like a fancy way of saying,
Okay.
make a good initial guess
At what?
at what the high-resolution weather will look like
Okay.
based on the coarser data we have.
So you take the big picture
Yeah,
and you try to fill in the details.
right.
Yeah.
And they use a special type of neural network for this.
Which is?
It's called a UNet.
a UNet. Okay.
It's basically just a really powerful tool for this kind of image-to-image prediction.
So you feed it the blurry big picture, and it tries to create a sharper image.
Exactly.
So that's step 1.
Now, step 2 is where it gets really interesting.
Damn me.
This is where the diffusion model comes in.
Okay.
So it learns to predict the residual correction.
Residual correction meaning?
It's the difference between that initial guess from the UNet
Right.
and the actual high-resolution weather we want.
So it's like fine-tuning.
Exactly. It's cleaning up the initial prediction.
Okay.
And by having the diffusion model focus on just this leftover part,
Okay.
it can actually get better results.
It's like a specialist.
Right. It's not trying to do everything at once.
It's focusing on what's missing.
Exactly.
Clever.
And the researchers mentioned this cool connection to fluid dynamics.
Oh, really?
Yeah, they said this two-step idea was inspired by something called Reynolds decomposition.
Reynolds decomposition.
It's this thing used in studying fluids and climate data
Okay.
to separate the average flow from the turbulent fluctuations.
So they're applying this concept to weather forecasting?
Yep. Yeah.
I like that.
So to test out Cordiff, they used historical weather data for Taiwan
Okay.
from this thing called ERA5 reanalysis.
ERA5 reanalysis, what's that?
It's like this really comprehensive record of global weather,
Oh, cool.
and they fed the model low-resolution data,
How low are we talking?
like a 36 by 36 grid,
Okay.
and then they wanted it to predict the weather at a much higher resolution,
Not much higher.
448 by 448.
Wow, that's a huge jump.
Yeah, big time.
So they're basically taking this blurry historical picture
Right,
and seeing if their model can generate something that looks like a state-of-the-art model.
Exactly.
At a way finer scale.
right.
And did it work?
Okay, so they compared the Cordiff predictions
Okay.
to data from the CWA-WRF simulator.
What is that?
It's this really detailed weather model used by the Central Weather Administration of Taiwan.
So it's like the gold standard for them.
Yeah, pretty much.
Okay.
And the results are in their Table 1 in
Yeah.
the paper. Cordiff did really well.
How well?
It got a better score on the CRPS.
Okay, but remind me what CRPS is again?
CRPS stands for Continuous Ranked Probability Score.
Okay.
It's like a key way to measure how good probabilistic forecasts are.
The lower the better.
Yeah, exactly. Lower means more accurate.
Okay.
And it also performed just as well as other methods on the mean absolute error,
Yeah, AE.
which is another common accuracy measure.
Okay, got it.
And importantly, it beat out simpler methods,
Mike, what?
like just using the raw low-resolution ERA5 data,
Interesting.
or using just the UNet model without the diffusion part.
So the 2 steps together are really important
Yeah, they worked better together.
for predicting things like.
Like how strong radar signals would be temperature wind.
Cool.
And they even checked to make sure these improvements weren't just random.
They were statistically significant.
Yeah, statistically significant,
Okay, that's a good sign.
right? It means there's something real going on.
So no model is perfect, though, right?
Of course not.
Where could Cordiff improve?
Okay, so they noticed that it had some trouble predicting how much the radar signals would vary.
The variance?
Yeah, at larger scales, bigger than 100 kilometers, it underestimated the variance.
Okay.
But then at smaller scales, between 10 and 50 kilometers, it overestimated it.
So it was a bit off on both ends.
Yeah,
Mm-hmm.
which suggests the model's probability distribution for radar reflectivity was a little too spread out.
A little too uncertain.
Yeah, kind of.
What about the ensemble predictions?
Okay, so those are the multiple forecasts that give us a range of possibilities.
Right.
They found that those were a bit underdispersive,
Underdispersive.
meaning the range of those forecasts is a bit too narrow compared to the actual errors.
So the model's a little too confident.
It thinks it's more accurate than it really is.
Got it.
It said this is something we want to work on in the future.
Okay. So they're aware of that.
Yeah.
Now, they also talked about a specific case study in the paper.
Oh, yeah, the frontal system.
Yeah, what was that all about?
So they looked at a cold front.
A cold?
You know how those bring big changes in temperature and wind?
Yeah, and often rain.
Right. So the high-resolution data from the WRF model,
The detailed one.
yeah, it clearly showed the sharp boundaries of the front,
Okay.
but the lower resolution ERA5 data kind of blurred it out.
Made it less defined.
Yeah. And Cordiff was actually able to restore some of that sharpness
Oh, wow.
in the temperature and wind fields.
So it was able to pick up on those fine details
Exactly.
that are really important for understanding how the front will impact things.
Right. And what was really cool was that the radar reflectivity predicted by Cordiff,
The strength of the radar signals?
yeah, it was concentrated near that sharper frontal boundary,
Makes sense.
right in the colder air.
Which is where you'd expect it to be.
Yeah, so it seems like the model is learning to connect different weather elements in a way that's physically plausible.
So it's not just spitting out random numbers.
No, it's actually learning something about the physics.
That's impressive.
They did note, though, that this sharpening skill varied a bit from case to case.
Okay, so it's not perfect.
No, but it's promising.
Now, one of the big things people talk about with machine learning is speed.
Speed and efficiency.
How did Cordiff do in that department?
Okay, so they compared how long it took to run Cordiff on a single graphics card
Okay.
to running the operational CWA WRF model on hundreds of CPU cores.
A single graphics card versus hundreds of cores.
Yeah, and for a single high-resolution forecast, Cordiff was about 500 times faster.
500 times faster.
Yep, and it used 10,000 times less energy.
Wow, that's amazing.
That's like a massive difference.
Huge.
And they pointed out that because each Cordiff forecast is calculated independently,
Okay.
you could run a whole ensemble of forecasts in parallel.
On multiple graphics cards.
Exactly, and that would speed things up even more.
So a forecast that used to take hours on a supercomputer,
Could be done in minutes.
that changes everything.
It really does.
Okay, so now let's switch gears a bit and talk about this other paper.
Okay.
The one with GenCast
Right.
for global probabilistic forecasting.
This is the one that's trying to predict the weather for the whole world.
Yeah, 15 days out
Ambitious.
at a resolution of 0.25 degrees.
Okay, and what's the big claim?
The big claim is that GenCast performs better than ENS,
ENS.
which is the ensemble forecast system from the European Center for Medium-Range Weather Forecasts,
Oh, wow.
which is considered the best operational medium-range forecast system in the world.
Okay, so they're saying they're better than the best?
Yeah, pretty much.
Bold statement.
And they back it up with data.
They do?
Yeah, they say GenCast outperformed ENS on 97.2% of the 3,320 different weather variables and locations they looked at.
97.2%. That's pretty impressive.
Yeah, it's a big deal.
So how does GenCast do it?
Like, what's going on under the hood?
Under the hood.
Yeah.
So it's also built using a conditional diffusion model.
Okay, so similar to Cordiff in that way.
Yeah, but this one was trained on 40 years of global weather data.
40 years.
Yeah, from 1979 to 2018.
That's a lot of data.
Tons of data.
Crazy.
So they fed it over 80 different weather variables.
At the surface and in the atmosphere.
Yeah, 13 different levels in the atmosphere.
Wow.
And then, just like we talked about with diffusion models,
Start with noise.
start with random noise.
Refine it.
Refine it step by step.
Until you get a forecast.
Exactly. And by starting with different random noise each time,
You get an ensemble.
we get an ensemble, a range of possible scenarios.
Okay, and they say these forecasts look realistic.
They do. They're
Yeah.
very detailed, and they have that natural variability we see in real weather.
So they pass the eye test.
Yeah, they look like the real deal.
How about accuracy, though?
Okay, so they compared GenCast to ENS.
Using the CRPS score again.
Right. And GenCast showed significantly better skill than ENS for most of the targets they looked at,
Most
like
MEA.
the vast majority,
Wow.
especially for forecasts up to about 3 to 5 days out.
So the shorter term forecasts?
Yeah. And it was particularly good for surface weather.
Like temperature, wind.
Yeah. And also for temperature and humidity higher up in the atmosphere. They did mention that they didn't include precipitation in their main results
Why not?
because they had some concerns about the quality of the precipitation data in the ERA5 dataset.
Okay, so that's something to keep in mind.
Yeah, just a caveat.
But still, even without precipitation, that's a lot of stuff that GenCast is better at.
Yeah, it's a big win.
So they're accurate, but how about calibration?
Calibration.
Yeah, does GenCast know when it might be wrong?
Oh, that's really important.
It is.
A good probabilistic forecast should be well calibrated.
Meaning?
The probabilities it gives should match how often those things actually happen.
Right.
And they found that GenCast is actually well calibrated,
Good.
similar to ENS.
So it's as good as the best in the world
Pretty much.
in terms of knowing how certain it is.
Right.
Now, they also looked at extreme weather events.
Oh, yeah. This is where it gets really interesting.
GenCast was good at predicting extremes.
Yeah, it was significantly better than ENS at predicting things like extreme high or low temperatures
Okay.
and very strong winds.
So the rare stuff.
The really high impact events.
The stuff we really need to know about.
Right. And they used a measure called relative economic value to assess how valuable the forecasts were for making decisions.
Okay.
And GenCast showed better REV across a variety of different scenarios.
Mean.
It would be more useful for making decisions about things like evacuations or resource allocation.
So if we had GenCast, we might be better prepared for those extreme events.
Potentially, yeah.
That's huge.
It's a big deal.
And it wasn't just about single locations either.
Right.
They also looked at how well GenCast captured weather patterns across different areas.
Yeah.
Yeah, weather doesn't just happen at one point.
No, it's all connected.
And GenCast was better at predicting average and maximum conditions over various spatial scales.
So it has a good grasp of the bigger picture.
Yeah, it sees how things are connected.
It does.
And they also looked at some specific applications,
Like what?
like predicting wind power generation. Yeah, they wanted to see if GenCast could accurately forecast the total amount of wind power that could be generated.
Across a whole region?
Yeah, with multiple wind farms.
Huh.
It did better than ENS.
That's great.
Yeah, it could be a really valuable tool for managing renewable energy.
Makes sense.
And of course, they also looked at tropical cyclone prediction.
Hurricanes and typhoons.
The big ones.
Yeah, high stakes.
So how did GenCast do?
Really well. The average track of the cyclones predicted by GenCast was more accurate than ENS.
So it knew where they were going better.
Yeah, and it gave us about a 12-hour advantage in accuracy.
12 hours, that's a lot of time to prepare.
It could be the difference between life and death.
Yeah, it could be huge.
GenCast was also better at predicting the probability of a cyclone track falling within a certain area.
So it gave you a better sense of the potential risk.
Exactly.
Really important stuff.
Life-saving stuff.
Okay, so we've talked about Cordiff and GenCast.
Two very impressive models.
Now, what about that third model we mentioned?
For GrassCast.
RAFCast, yeah.
So this one's also a global model,
Predicting weather up to 10 days in advance.
but it's super fast.
How fast are we talking?
It can generate a 10-day global forecast in under a minute.
Under a minute.
Yeah, using a single Google Cloud TPU.
That's insane.
It's crazy fast.
So what's the catch?
Well, the main thing is that it's deterministic.
Meaning?
It only gives you one forecast,
Okay.
not a range of possibilities like GenCast,
Got it.
but it's still incredibly accurate.
Like how accurate?
It beat the European Center's most accurate deterministic model.
The same group that makes ENS.
Yep, on 90% of the targets they looked at.
So it's basically the best single outcome model out there.
As far as we know, yeah.
And it uses graph neural networks to do its magic.
Yeah, it's a pretty complex architecture.
But it works.
It does.
So we have Cordiff GenCast, GraphCast,
Three very different approaches.
but all using machine learning to push the boundaries of weather forecasting.
It's really exciting to see.
So let's recap the key differences for our listeners.
Okay, sounds good.
Cordiff is all about those super detailed local forecasts.
Kilometer scale.
It uses that two-step process with the diffusion model to refine the predictions.
Right. Get those fine details.
GenCast is global probabilistic,
A range of possibilities.
and it's outperforming the current best global probabilistic system.
That's a big deal.
And GraphCast is global deterministic.
One single best guess.
Super fast and more accurate than the top single outcome model.
So yeah, 3 very different tools for different jobs.
And the thing that's really striking to me is that we're now seeing these probabilistic forecasts
Like GenCast.
actually beating traditional methods.
Yeah, that's significant.
Because being able to understand the uncertainty in a forecast,
And get a sense of the range of possible outcomes,
that's crucial for making good decisions.
especially when it comes to things like extreme weather
Right. We need to know what the risks are.
and what the best and worst case scenarios might be.
Exactly, so we can prepare accordingly. And the researchers talked about how these technologies could be improved even further,
Oh yeah, there's so much potential here.
like using even higher resolution training data,
That would be awesome.
finding ways to make the models even more efficient,
Squeeze out every bit of performance
and fine-tuning them with real-time operational data.
so they're constantly learning and adapting.
It's really incredible to think about what the future holds.
It is.
Okay, so for our listeners out there,
What should they take away from all this?
the big takeaway is that machine learning, and especially these diffusion models,
Those are the real game changers.
they're making huge strides in how we predict the weather.
Absolutely.
We're seeing forecasts that are faster,
More accurate
more nuanced,
and more useful.
and models like Cordif and GenCast.
The ones we talked about today.
They're showing us that machine learning can outperform the traditional methods in a lot of important ways,
Like what?
like providing really detailed local forecasts,
Right down to the kilometer scale.
improving overall forecast accuracy worldwide,
So it's not just about specific locations.
giving us better predictions of extreme weather,
The stuff that really matters.
and even enhancing our ability to track dangerous storms.
Like hurricanes and typhoons?
It's a whole new era of weather forecasting.
It really is.
So, as you think about all of this,
What should our listeners ponder?
consider how these advancements might change things in various sectors.
Like what?
Like farming, energy production, disaster preparedness.
Even our daily lives.
How might probabilistic forecasts and better predictions of extreme events impact those areas?
Yeah, that's a great question.
What new opportunities might arise?
And what new challenges might we face?
We encourage you to check out the research papers we talked about today
If you want to dive deeper.
and think about the broader implications of AI in climate science.
Yeah, this is just the beginning.
Thanks for joining us,
That was fun.
and stay tuned for more deep dives into the cutting edge.
See you next time.